Good morning, everyone. We see that a lot of people are now connected to this webinar, but maybe we can wait just 1 minute more in order to start. So first of all, a very welcome to all the people that are already with us today to this webinar dedicated to the discovering of V-tremors through our BIOMAPS project. So very welcome to everyone to this first webinar dedicated to the discovering of V-tremors through our European project BIOMAPS. Today we're here with several speakers, and we hope we will introduce you this innovation in an engaging and let's say interesting way through this meeting. Just some few words before starting. We invite you during all the webinar, if you have questions for us, to write them in the Q&A chat in order to pose this question after all the presentation to our speakers, and interact please with the chat with us. In the meantime that someone else is still connecting to this webinar, maybe we can start the activities with a first ice-breaking activity, so with the 1 or 2 questions dedicated to a poll. So maybe we can ask you if you want to share with us if you already know what V-tremors are. This could be interesting for us to understand your background, and if you already know something about this, or if everything will be completely new. The second question is, do you know the difference between the bio-based and biodegradable materials? And the third one, if you already know what are V-tremors, which application or sectors do you think are relevant for the bio-based V-tremors? So if you want to share with us your point of view, we will be glad to investigate a little bit about this in order to also set our presentation and hopefully make it be as much engaging as possible to provide you all the information for learning something new today. We have a quite acknowledged and expert public, because a lot of people, 70% of people said that yes, they already know the V-tremors and already have had some experience on these. Instead, just 30% said no. So a quite expert audience. Do you know the difference between bio-based and biodegradable? Yes, so 90%. Well, so we won't spend so much time to investigate and deepen information that you already have. And the last one, so which applications? The first one, the biggest one, is the packaging, then automotive, electronics, biomedical, healing. That is not really an application, but we could say maybe a property, but we will see this in a more complex and detailed way during the webinar. Adhesive, industrial applications, coatings, for actuators, thermosets, I think that batteries. So we have a lot of different alternatives and different possibilities. So we will say if all these hypotheses match with the possible uses of V-tremors during this presentation. So another welcome to all those who just connected to this presentation and this moment together. I think we can start right now with the presentation of the BIOMAPS project. So
thank you, Doriana. So a couple of words about myself. So I'm Antti Puisto. I'm a research team leader at ETT, the Technical Research Center of Finland, and I'm leading a team focused on soft condensed materials modeling. And I'm here giving this talk as or in the role of BIOMAPS project coordinator. So let me start from the, let's say, a bit of the background of this whole project. So when we look at bio-based biodegradable plastics, so here specific focus is on PHAs, we can see a lot of opportunities in their application. I mean, if they could be used for as wide as possible application areas, we could see a lot of good development in the sustainability of the society. So, for instance, the reduction of plastics and microplastics accumulation, because they are biodegradable, they have certain flexibilities in their production, so they can be produced using the biosynthetic methods out of various feedstocks. So this, of course, gives the opportunity to, let's say, distributed production of these materials and also utilization of different raw material streams. In part, PHAs have not been adapted by the plastics industry because they have certain problems in their manufacturability, for instance. So it's not on the level of traditional thermoplastics in a way that many of these PHAs, they have melting temperature and degradation temperature quite close or not, and sometimes even matching each other. So this means that whenever you process these materials, they tend to change their properties. And of course, some of the properties for the final products are not on par with the application demands. So this has risen sort of the motivation for having a project such as BIOMAPS. So we started looking at this problem from the point of view that if we take a thermoplastic biodegradable material and try to improve the properties and the processability by vitrimerizing the material, so introducing non-permanent cross-linking. Traditionally, permanent cross-linking for such materials have been used, but the recycling properties of these are then, of course, lost. So then this leads to a situation where we have a transition temperature between thermoplastic and thermoset behavior. So at high temperatures, these materials remain thermoplastic, while at low temperatures, they have the good qualities of thermosets. So great thermomechanical stability, chemical resistance, and so on and so forth. So these ideas led to the BIOMAPS project that we are discussing at the moment. So BIOMAPS comes from this longer name, Biointelligent Manufacturing of Multifunctional Bio-based Polymer Systems. And here is a link to our project website. So our mission is basically to develop a fully circular manufacturing value chain for such biomanufactured plastics. And these materials are expected to retain their mechanical recyclability and biodegradability, and of course introduce another set of different functionalities, such as, for instance, self-healing. And of course, for the developments that we do experimentally, we support them using AI-based tools, and we want to speed up the adaptation of these materials for the manufacturers in the long run by developing also tools for the adaptation in different kinds of processes. This is the project consortium So we have a good collaboration between academic and industrial partners. Altogether, we are 11 partners involved in the project. And this is the first year that's coming to an end in the end of this month. Here is the rough project structure and the roles of the different partners. And as you can see, we have industrial and academic players in the development of the technologies and also in the demonstration cases. The project coordination is with VTT, as I mentioned before, and the digital tools are also developed at VTT and also University of Turku. So if we sort of coarse grain the description of the project, we can say that we have 4 main phases. So we have the synthesis of the PHAs from bacterial sources. We have their vitrimerization, the overall characterization, and their adaptation to manufacturing technologies. And then we have the assessment of the biodegradation and biosynthetic recycling, and those possibilities and options. We support these developments using AI and modeling tools. So basically, the PHA production process is optimized using AI tools. The vitrimer design will be optimized using different kinds of physics-based models and AI tools together. We provide digital models for manufacturing and optimization. And then, of course, we gain fundamental understanding of the degradation phenomena using the synergies of experiments and models. We have the 3 demonstrators, and these are not completely locked in yet, but what we foresee is an automotive use case. So we replace an interior bulk component, which is typically made of PCABS, with a vitrimerized PHA composite. We have a battery use case where we use the vitrimerized PHAs as separators or binders for electrodes in lithium-sodium-based batteries. And here we use film casting to manufacture these. And then in flexible electronics, we foresee several different use cases. For instance, protective self-healing films or seeds for selected components by film extrusion. And finally, just a couple of words about the impacts that we expect from the project. So we expect to find innovative approaches for controlling the manufacturability and the properties of these PHA-based components. So using the vitrimerized materials, we foresee that there's possibilities to use different types of manufacturing approaches which are not available for the current PHA materials. And of course, the optimization of resource utilization that comes from fully circular material loops is of course a given. And this will reduce, of course, the material costs for the PHAs, because if we can reuse them, then the production costs are not that significant.
Let's go through this topic of sustainable materials, and today with my colleagues, Professor Beatrice Lerma and Dr. Vanessa Bruno from Politecnico di Torino, we will try to introduce you the topic of being sustainable in design-driven materials. Our point of view, our perspective is from the perspective of design, because we belong to the Department of Architecture and Design, and we would like to first of all introduce you these frameworks in which innovative and sustainable materials have been more and more developed in the last years. We all know that Europe is working with big efforts to develop sustainable materials, aiming at those targets of climate neutrality, circular economy, reduction of waste, and responsible resource management. Every one of us, for sure, has heard some of these concepts during the last decades. We always speak and we heard a lot about the European Green Deal, the bioeconomy and bio-based materials, the LCA, the new European Bauhaus, the ESG. But we thought that in order to better investigate the role of vitrimers, we really had to try to understand, first of all these frameworks that have been developed by the European Commission along the last decades in order to push this innovation forward in the idea of pursuing sustainability, especially with new materials. Some of those frameworks, like the Green Deal, the New European Bauhaus, and the ESG, are, let's say, mainly political frameworks. So they define the direction and the governance in order to establish basically economic and cultural priorities of the European Union. Some others are methodological, like the LCA, and are used to measure and verify the sustainability of an innovation, and especially to introduce quantitative assessments. Some others, we can call them design frameworks, are a kind of guidance to the design of materials and products. So they are thought to influence industrial design and architecture. And the last one, like bioeconomy, bio-based materials, and the topic of material sufficiency, are, let's say, cultural and critical frameworks to question the production paradigm and to make research and industry shift the focus from efficiency to consumption reduction. To better understand all these frameworks that sometimes are also a little bit complex, we try to provide a global overview of this evolution, again splitting them between these 4 different typology of frameworks in order to make them comparable, also declaring the implicit question behind every framework that have been developed, and the key concepts, the scale of intervention, and the main criticism. But of course, the most important framework for our BIOMAPS project is this last one of the bioeconomy and the bio-based materials, in which vitrimers from PHA have been developed and are that we are developing right now. So the topic is, and the main question is, how can we manage these biological systems and replacing extractive fossil systems? And the key concept is renewability, and the typical tools of this kind of paradigm are biomaterials, of course, but also biofabrication, in order to push industry and agriculture toward these new directions. Regarding these bioeconomy and bio-based materials, some are the main strategies and policies that the European Union has focused in order to push forward these innovations, like the Circular Economy Action Plan, that is foreseen to be applied for 2030, and the Safe and Sustainable by Design framework and strategy. That are, we can say, the 2 main pillars in these innovations. But what does it mean for European citizens to have these kind of new materials? We always, as I was saying before, watch this topic and observe this topic from the design point of view and from the final consumer point of view, the end consumer point of view. So the naive people that represent the civil society and that discover these kind of materials when they are on the market, and sometimes, hopefully, also when they are developed during the research stages. But of course, that people that is naive and that has a duty to, let's say, ensure to guarantee the sustainability throughout the entire life cycle. So not just during the use of these materials, but also to the disposal phase. And in order to better understand these materials, we strongly think that watching not only to technical performances, but also to user experience, aesthetics, and emotional and cultural values is very important to make people be more aware about the innovation. In this context, two different approaches are central for a correct use of materials, of the development of the materials, and the adoption of materials in the design process. That are the design-driven materials approach and the material-driven design approach. Two different approaches that differ from the position of the words, but also a lot in the development of the materials and of the production, of the manufacturing of end products. The design-driven materials approach is a methodology that places design and not just the engineering performances at the center of the material innovation. So this is important to involve also perceived used to involve also the perceptive characteristics of the material in its development, but also consider how we can shape new products involving the materials and their perception during the use, during the integrated, let's say, social context. Instead, the material-driven design approach is a methodology in which experiential and expressive qualities become the starting point of the design process. So this means that we don't adopt the material and choose the material right at the end of the development of the product, but really at the beginning of this process. And this is important because it allows to involve not only technical but also sensory, emotional, and experiential characteristics into the design process as the beginning.
Yes, thank you. And we go more in deep in this wide world of materials, and in particular we try to understand how the words materials and sustainability could be read. In fact, environmental impacts occur at the different stages of the life cycle, including the production, the transportation, and processing of raw material, and at the stage when the product is used and disposed of. But we have a different way to describe sustainable material. For example, bio-based materials, recyclable materials, but also circular materials that could be considered also a synonym for bio-based material or for recycled material. Such a way of classifying is neither sufficient, not complete. In fact, we have to consider that material have their impact on the environment, of course, through their entire life cycle. But we have to consider how they are used. And so we have to choose the right material for the right products. So we have to consider a material integrated into the entire application systems. And then, of course, we are speaking in this project about bio-based material, and we try to define these materials. So the bio-based materials are defined as material made wholly or partially from renewable biological resources, for example, plants or animal or other organism. And these material don't use non-renewable fossil fuels. But we have to consider that this material could not be always biodegradable. And what about the right choice of the right materials for the right products? So we have to take in account the life cycle of the product where we use a material or more than one material, of course, because the application is the crucial moment in which we define the product's environmental impact. In fact, the 80% of a product's ecological impacts are defined during the design phase. So, for an application is not simply a matter of choosing a material, but it defines its entire life cycle and the integration in a complex production systems. Here we can find a proposal of definition of bio-based materials. In fact, biomaterial is the broadest terms, and it simply means any material that has a biological association. But we can have more specific terms and more specific terminology that define the bio-based material, biosynthetic or bioplastic materials, and the biofabricated materials. So, for example, the biofabricated materials are made by growing living cells and microorganisms. And the biosynthetic or bioplastic material are synthetic materials made from a biological source. So it's quite difficult to navigate, to move inside this wide world of sustainable materials, of course, but also inside the world of biomaterials or bio-based material, because we have many different characteristics that define that can define different application and different products development. Another key point of the biomaterials is, of course, the interaction between material properties, production methods, application context, and end-of-life scenario. So we have to consider that to develop, to introduce on the market bio-based material needs an integrated approach to different aspects of the life cycle of this material, but also to very complex systems. And also these complex systems are not only considering technological aspect, but also cultural aspect. In fact, bio-based material often still lack a shared aesthetic language and strong identity. And the question is if they will ever get it, because the study on the sustainable material identity, and the identity in particular of industrial material, it's very complex. So we can consider some key points, key concepts about how to develop this identity and to gain a broader acceptances of this material. And these key points could be the material authenticity, so the how we can consider the truth of a material in relation to its origin, composition, but also the expressiveness of these materials, the imperfection that could be an identity way to understand the material, and also biological traces as value. And again, some points that can be considered when we go to understand materials and giving them an identity are time, temporality, because bio-based materials are not static. Again, the origins of these materials, because they can carry traceable and narratable origins from agricultural waste, from mycelium, from bacterial. Also, we have to consider that they have an agency that becomes a key point, a central role, because they can be considered as active systems. And again, they can have a cultural identity. They can not only be considered as a sustainable alternative, but they can have shared aesthetic codes. And as designer, we can work on these aesthetics codes and this identity of these new materials.
So following the trends discussed earlier, adjectives such as organic, natural, eco-friendly, and green have appeared on many products over the year. They are all terms used in the marketing to associate the product or service with concept of sustainability, safety, lower environmental impact, and ethical production. But is it all true? Sometimes these claims are very vague or unverified. This practice is known as greenwashing, which is the deceptive marketing tactic of making a company or product or a policy appear more environmental friendly or sustainable than it actually is. There are tools available to help us determine whether greenwashing is taking place. One tool is the LCA, the life cycle assessment, which allows us to assess the entire life cycle of a material or product from its extraction and production to its transportation, use, and finally disposal or recycling. This final phase of recycling or disposal is essential for closing the loop, transitioning from a linear to a circular flow. Designing for sustainability also means designing for end user behavior, because products should help users make the right choice. Now let's take a look at some best design practice that make a design a good design. The first one is the choice of material, obviously, which should be sustainable, and this is linked to the field of material-driven design. Good graphic design focuses on providing clearer but also understandable instruction and labels for everyone. How many times have you been not sure where to dispose packaging? These case studies that you see in the picture make it very clear that the packaging must be like peeled apart to separate the two materials, components, for a proper disposal. Another best practice is designing for disassembling, which involves designing an object so that it is easy to maintain, but also to repair it. If a part broke on your mock-up pot, would you throw it all away or just replace the part? Probably the second. Finally, good design is intending to be long-lasting. How many products do you have that you will never throw away like these because they are durable but also have an evergreen style? So for concluding, all this for saying that good design lasts.
And again, we can put in evidence that materials have a crucial role in design process and in the product development, but they can help to define strategies and policy to promote sustainability, circularity, and regenerative approaches. And we have also to consider that innovative materials can help to reduce the numbers of components and material by developing new technical properties and characteristics.
Thank you, Beatrice. A couple of words about me. I am Daniele Nuvoli, Associate Professor at University of Sassari, and my research field is in the synthesis and characterization of polymers. To understand the potential of vitrimers, we can start from environmental sustainability issues related to the use of plastics. As example, in 2004, more than 400 million tons of plastics were produced. And if we take a look to the life cycle of plastics, we can see that we can produce plastic from petroleum or biomasses. We can obtain thermoplastics or thermoset polymers, and after they use, only the 10% of plastics is recycled, thermoplastic polymers. The other part, 90%, is confined in landfill or burned in incinerators, and this represents an environmental problem. The ideal life cycle should be a life cycle in which we have 100% of recycled plastics. As Antti said, we can classify polymers, so plastics, in two classes: thermoplastic polymers that have linear or branched structure. They are not cross-linked, and they can be easily reshaped and recycled by heating, but they have poor mechanical properties. On the other hand, thermoset polymers are cross-linked. They have very good mechanical and thermal properties and also chemical stability, but they can't be melted or recycled, and this is an environmental issue. By considering this context, vitrimers could represent a turning point in the plastic production, in the plastic of the future. But what are vitrimers? They are polymers made of covalent adaptable networks, CANs, that contain thermally activated dynamic covalent bonds. As you can see in this scheme, we can have two situations. Below a certain temperature, vitrimers behave as a normal cross-linked polymer, so like thermoset. Above a certain temperature, there is the activation of dynamic covalent bonds, so there is a rapid exchange in these bonds, and we can observe the peculiar vitrimeric properties, so we can reshape and modify the shape of vitrimers. We can also state that vitrimers can bridge the gap between thermosets and thermoplastics. They have the advantages of thermosets, so they have very good mechanical and thermal properties, and they can be also melted and recycled. This is due to the dynamic covalent bonds cross-links. We can represent these bonds like padlocks. When the padlock is opened, we have a situation similar to thermoplastic. When padlock is closed, we have a polymer similar to a thermoset. We can classify vitrimers and cans into two classes. Dissociative cans. In this type of cans, the existing bond is broken before a new one is formed. So we have a moment in which the molecular fragments are free. So there is a temporary decrease in cross-linking density during the exchange. And this happens when polymer reaches a certain temperature. The risk is that material could lose structural stability. In associative cans, we have another type of behavior. The new bond is formed before the old one is broken. So we have a constant cross-linking density. There is never a moment when the polymer is disconnected and the material doesn't lose structural stability. These associative cans are considered, in fact, the true vitrimers. To better understand the behavior of vitrimers, we can also define two transition temperatures. The first is glass transition temperature. It's common in polymers and represent the temperature at which there is a shift from a glassy to a rubbery state. As example, we can consider latex gloves. If we put latex glove into liquid nitrogen, so very low temperature, we can observe that we obtain a fragile material that behaves like glass, so it's brittle. At room temperature, so above TG, we know that latex gloves behave like an elastomer, so we can modify the shape. The other temperature is topology freezing transition temperature, and is typical of vitrimers, represent the temperature above which the bond exchange reaction becomes rapid. This allows the material to reorganize and flow. In general, TG is lower than TV, and between these two temperatures, vitrimers behave like elastomer or rubbers. Above TV, we can see that there is a decrease of viscosity, a gradual decrease, and this behavior is similar to the behavior of glasses brought to high temperature. In this zone, we can reshape the polymer like glasses at high temperature, because vitrimers behave like viscoelastic liquids in this zone. So we can summarize this behavior by considering this picture. At the temperature below TV, we have a locked state. The topological lattice is frozen, dynamic bond exchange slowly, and we have a situation like a thermoset. Above TV, we have the activation of dynamic covalent bonds, and we have a viscous flow in which we can see a topological rearrangement. We can change the shape of the vitrimer without changing the cross-linking density. To obtain vitrimers, we must use specific functional groups and reactions. Without going into details of chemical reactions, we can see that they are equilibrium reactions in which we have exchanges in specific groups. These reactions are disulfide exchange, imine metathesis reactions, transesterification reactions, boronic ester metathesis, and Diels-Alder reactions. These last two are being used in BIOMAPS project to obtain PHEA vitrimers. Dynamic covalent bonds impart vitrimers peculiar properties. We have seen that they are recyclable. They have also shape memory properties, so we can fix a permanent shape, change this shape into a temporary shape, and re-obtain the permanent shape by a thermal switch. They have also adhesive properties. We can glue different layers of vitrimeric materials. And finally, they have self-healing properties. So we can cut vitrimers into various pieces, or we can scratch vitrimers. And if we put in contact these pieces, we can observe a self-healing process. If we reconsider the first slide, so the life cycle of plastics, the use of vitrimers can permit us to close the loop. So by introducing dynamic covalent bonds into polymer backbones, we can completely recycle the plastic materials because the presence of dynamic covalent bonds that can permit to recycle and reshape polymer. This is very good in terms of sustainability, and we can further increase sustainability if we use only bio-based materials. So we are talking about bio-based vitrimers. They exploit renewable resources, so vegetable oils, cellulose, starch, agricultural wastes, and so on, significantly lowering carbon footprint. We obtain materials that are potentially recyclable, compostable, and biodegradable. And we can exploit chemistries and industrial plants that are optimized for the fossil-based counterparts. In BIOMAPS project, we are using polyhydroxyalkanoates. They are particular polymers that are produced by specific bacteria. They have an energy, they behave as an energy source for bacteria, and they are stored in intracellular granules, as you can see in this picture. Finally, I can show you the general scheme of BIOMAPS project. So we can see that polyhydroxyalkanoates are produced by using specific bacteria, feeding them with carboxylic acid containing double bonds. This permits to obtain polyhydroxyalkanoates with unsaturation in the side chains, and this unsaturation could be exploited to link cross-linker that impart to the polymer vitrimeric properties. So we obtain PHEA vitrimers. These vitrimers then will be tested. Particular vitrimeric properties will be tested. So thermal reprocessing, the possibility of the the networking, and also the biodegradation properties. Okay, this is all from my side. Thank you for your attention.
My name is, I'm Ana Otero. I'm from the team at the University of Santiago de Compostela in Spain that will be assessing the biodegradability and recyclability of these new polymers that will be produced in BIOMAPS. So just to put the problem in frame, I'm sure many of you have already seen this figure many times. It's the problem of non-biodegradable plastic accumulation in the environment. Right now, we have the estimation is that we have accumulated something like 10 billion tons of non-biodegradable plastics of petrochemical origin. Current production of this type of plastics is above 400 million tons and is expected to be increasing exponentially in the coming years in the world. The situation in Europe is a little bit different because in Europe we are more environmental conscious. We have consumers that are beginning to be concerned about this, and also we have a legislation that is trying to curb this tendency. So indeed, in Europe, we have a tendency to decrease the production of petrochemical plastics. But of course, to do that and to continue the decrease that you can see is very mild so far, we need new biodegradable plastics. And that is why where BIOMAPS is positioned, okay? So just to give you some key definitions, because you have heard about the definition of biomaterial, but for bioplastic, the official recognized definition of bioplastic is a little bit confusing and not so clear, because bioplastic is a bio-based plastic. That means it has been synthesized using organic molecules of plant or bacterial origin. That means from living organisms. And most of them, but not all, are biodegradable. But a bioplastic is also a plastic of petrochemical origin that can be biodegraded by microorganisms. So the confusion here is that not all bio-based plastics are biodegradable, and some petrochemical plastics are considered bioplastic because they can be biodegraded. So how important are these biodegradable plastics right now in the global market? Very low. If you remember, 430 million tons produced every year. Biodegradable plastic are around a little bit over 1 million tons. So a very small fraction of the market right now. And it needs to be increased, especially in Europe, to cope with the more restrictive legislations that we have. So first of all, how do we define biodegradation? This is key for designing new biodegradable plastics. So quite easy, biodegradable plastic is a plastic that can be attacked or converted by microorganisms to small organic molecules and CO2, mineralized, we say in biology. But for legislation purposes, the most important concept right now is compostable plastic. That is a plastic that will biodegrade under the composting conditions. These conditions are quite aggressive, probably the most aggressive that you can use to assess the biodegradability, because you will see high temperature, high organic matter, and also are the conditions that will resemble most waste treatment, organic waste treatment in Europe, right? But for bioplastic, really, when we are checking compostability, what we will check is, in most cases, disintegration. So the plastic will disintegrate in pieces that are lower than 2 millimeters in 12 weeks. This is what is being checked in most cases. So how do we assess this? So we have normalization institutes that tell us how to check that a plastic is a bioplastic. And well, these are the three most important ones: the American, the European, and the international ISO. And these institutions provide standard methods to assess the compostability or degradability of compounds that are used also by other national certification bodies that produce what we call eco labels. And most eco labels are certifying that the material that you have is compostable, can degrade under compostable conditions. So what are these standard methods? So these are the standard methods that are used to check biodegradation of plastics. Don't be afraid. I'm not going to explain all of them, just to show you how complicated it is and how many different standard methods and the specifications we have from different institutes. So these institutes produce two groups of norms. One are standard specifications. That means if you want to label like this, you have to make all these tests, mainly related to compostability, right? And then also produce standard methods. The standard methods are the detailed receipt of how you have to test all these characteristics. For those of you that are interested in looking at this in detail at these norms, I give you these two very good reviews that you can check in detail. But of course, I'm not going through all of these different types of biodegradation tests, just a few comments on the most common ones. Of course, as I explained, compostability is the most important characteristic that we have to demonstrate for a plastic. The specifications are not only about biodegradation, but to specify that you have a compostable plastic, you have to check some standard composition that you have toxic, disintegration, biodegradation, and also that your compost, the compost that you produce, is not toxic. But how do you check that? Well, you check that in testing standards. They are a little bit different depending on the institute, normalization institute that produce the test standard. But in general, this is the most aggressive way you can try to degrade a plastic. So that means presence of oxygen, of course, very, very high temperature. In fact, industrial composting very rarely reaches this high temperature, and very long time periods, up to 6 months. In most cases. And you just check if this is being mineralized to produce CO2. Another important test that is very common is soil biodegradation test, because especially for plastic of agriculture use, this is checked at much milder conditions, much lower temperature, and this test can last even for up to 2 years to check that the plastic is biodegradable under soil conditions. In both cases, it's very important to check the ecotoxicity, so that the products of the degradation of the plastic are not more environmentally dangerous than the original plastic. And you can do that by seed germination using the compost or the soil in which the plastic has been degraded. Or if you expect that the products of degradation go into aquatic environment, then you have to use different bioindicators, and all these tests are, of course, the standard methods to check the ecotoxicity of the results. Okay. These are the most important tests you have to perform, but not the only ones, because in some cases it's also important to check that your plastic can be degraded under anaerobic conditions, and you also have different testing standards to do that. In most cases, also very high temperature. And also it's important, of course, to check marine biodegradation, which is the mildest conditions, because you use low temperature, and also the testing lasts for up to 6 months in standard conditions. So this is what we have to do when we want to start to have an eco label for our material. But as you can imagine, these standard methods have an important limitation. One of them is reproducibility. Since the result will depend on the type of microorganisms that you have in your test around your testing material, it's difficult to obtain the same result in every condition. Here you see an example of the biodegradation with different soils, and you see the result is very different. Okay? Also, the test duration is very important. In the laboratory, it's not possible for us to keep the material for 2 years or 6 months to assess if that's the right material to go on with our research. But even at industrial scale, in most cases, compost or anaerobic digester do not keep the right time to obtain the same degradation that you get in the standard methods. Right? And most importantly, the conditions used in most of the standard methods are not realistic, because as you can imagine, you cannot obtain the same result in this big flash here that you have in the open ocean. So they are very serious withdrawals in using standard methods. So for research, we try to look for alternative laboratory tests, mainly to obtain faster results that can drive our research. In some cases, we use the isolated bacteria, pure cultures, and you can use plates with the polymer, and then check if the bacteria can eat the polymer of these clear zones. This is a very fast method, but it's difficult for some polymers, like for example, or the bitumers that we're going to produce in biomass. You cannot mix it with the agar and cultivate the bacteria on top. This is another test that we use in the lab, is the contact biofilm. So for this type of assay, you can use almost any kind of polymer. You just prepare a sandwich between the polymer and agar, which is not biodegradable, and the bacteria, to force the bacteria to attack the polymer. And with this test, you can get results about biodegradability in, let's say, weeks. To assess if there are some modification in the plastic, and also you can try to guess what will be the rate of biodegradation in the environment from these results. In the laboratory, we can also use more aggressive methods to assess the biodegradabilities. Here you can see 3 types of tests that we use in our lab to assess the biodegradability. Of course, oxygen is very important to facilitate bacterial growth, but not always. In some cases, results are even better in anaerobic conditions. And with these methods, you can obtain results about biodegradability in weeks or 1 month. You can assess if you can get changes in your polymer, and then the advantage is that you can use very different modes of presentation of your polymer, right? For these methods, you can use either isolated bacteria or bacterial consortia. For microbiologists, the use of consortium is a key way to go for degradation. And in the case of biomaps, as it has been already explained, we will produce the original material with bacteria, and then they will suffer bitumerization. And what we will do is to assess if the new polymers can be degraded, still keep the biodegradability features of the original polymer, and also if we can use the results of the degradation to feed the bacteria, and then establish a circular economy scheme. So since we have a new polymers, we are going to need new bacteria to be sure that we assess the biodegradability of these polymers. So what we're doing at Santiago right now is looking for new bacteria that are able to grow on these bitumers. We are using the same environments that you have seen before. So we are going to look in the marine environment for these bacteria, but we also want to try in a new environment that has yielded very, very interesting results in the past with non-biodegradable materials. And this is this type of larvae, insect larvae. These larvae, this is a species of phobas, but there are other larvae that can do that. They can eat plastic, petrochemical plastic like polypropylene or polystyrene, and they can grow on that. And it's not the larvae that are degrading the plastic, as the bacteria inside the larvae that are doing it. So this is a fine source of novel bacteria that can degrade plastic. And we have done that in the past and got very good results. Of course, it's very important that when you obtain the bacteria from the gut of the larvae, it's very important how you cultivate this bacteria to obtain a consortium of bacteria that is well adapted to your plastic. So just to give you an idea of what you can get, this is the bacteria in the gut of the worm. Every color is a different type of bacteria. Don't worry about the name, but you can see that depending on what you feed the worm, the bacteria will be different. Okay, when you extract the bacteria from the worm and then cultivate it, you can see the way you cultivate completely changes the consortium of bacteria inside, that you are cultivating on the plastic. And of course, if you use a different plastic, the bacteria will also be different. That will allow us to generate specific groups of bacteria that are are adapted to a specific plastic, and then we can use very fast to assess the biodegradability of material. You can see here is one trial in less than 3-4 weeks. We can assess the biodegradability and which is the consortium that is doing faster. So that is what we are doing right now for BIOMAPS. We are trying to find new bacteria and bacterial consortium that can degrade the new polymers, PHA-based bitumers that are being produced. And here you see our larvae that are eating the PHB in this case. And we already have adapted consortia and isolated strains that are able to degrade the original material, and we will see if they will also be able to degrade the bitumers along the project. And that's all on our side. Thank you very much.
So my name is Rafael Alonso, and I'm a researcher in AIM+, which is a technology center based focused on plastics based in Valencia, Spain. And among other activities, we are leading the work package in BIOMAPS, which is devoted to the development of the demo use cases. And so our goal is to demonstrate that bitumers can be innovative materials for advanced applications, right? And so these innovative materials, since they are representing a new paradigm in polymer materials due to their specific properties, they can deliver sustainability, durability, and also circularity to advanced applications, while maintaining performance. Since below the freezing temperature, the materials became cross-linked, and so they have these good properties still. And so we aim for three different sectors for our demo cases. First, the automotive sector. So this will be prototypes that will be developed by Opel Stellantis. We also aim for prototypes within the battery sector, which will be developed by Politecnico di Torino, and also some applications on flexible electronics, which will be done by INUR. So starting with the demo cases for the automotive sector, since automotive components require of high mechanical and thermal performance, bitumers can be good materials in order to substitute the already used materials in the automotive sector for materials which are better in a circularity point of view, so to speak. So bitumers are going to provide this structural integrity as thermosets, as the common materials that are employed nowadays. But additionally, they will the properties of self-healing will be beneficial in order to for example, to repair micro cracks or damage in these automotive parts. Additionally, since these materials are reparable, the lifetime of these parts is going to be extended. They are also reprocessable, and they are recyclable. And this will avoid other ends of life that are not desired, such as landfilling or downcycling, right? Additionally, the conclusion of all this is that B-trimmers will support the sustainability and circularity of these parts in the automotive sector. So more specifically, what we aim in BIOMAPS is to develop some prototypes for interior parts. Some are here shown in the picture, and the goal will be to validate these parts in comparison with the current standard materials that are employed nowadays, such as polycarbonate or ABS. We will also aim for demo use cases, which will be related with printed electronics. This will be done in collaboration between Inuru, doing the flexible electronic part, and Stellantis. And the prototype will consist in a door trim, or a central console trim, or headliner trim for interior applications in the vehicle. And this will allow to introduce capacitive sensors, sliders, or luminescence parts, and so on. Our second goal is to apply B-trimmers to batteries, more specifically to binders in batteries. Actually, B-trimmers are very highly promising solutions in order to increase the durability of the batteries, especially when under repeated cycling, right? And this is because the dynamic network enables stress relaxation. Also, the self-healing properties of B-trimmers will prevent the crack propagation, also helping in the increasing of the lifetime of the component, and actually maintaining the integrity of the electrode. And so, at the end of the day, we will have batteries that last longer and with more stable performance. Additionally, we have all these properties of the B-trimmers regarding the end of life, such as recycling and material recovery. It's also very interesting that our demo cases for the battery sector in BIOMAPS are based on PHA, because PHA has also very good properties regarding this application. Because PHA is known to allow strong adhesion between the active material and the current collector. It also maintains the structural stability of the electrode, also helping this long-term cycling and increasing the lifetime of the batteries. And additionally, they have high wettability, and this helps to binder helps the binder to the electrolytes, providing certain diffusion paths for the lithium ions. And this makes PHA as a good replacement, or a very prominent replacement for biodegradable fluorine-free PVDF materials that are using right now in the next generation of lithium-ion batteries. Our last demo cases are related with the flexible electronics sector. In this case, B-trimmeric materials are also very beneficial, since for this application you need high flexibility, also reliability, hydrophobicity, and durability. And B-trimmers can help in these aspects because they provide resistance to the repeated blending and deformation, and this is due to the properties, these dynamic properties that these materials possesses intrinsically. The self-healing is also very beneficial in this case. And also this will allow to maintain the functionality over time, also increasing the lifetime and durability of these components. Again, we will have very good benefits for these materials regarding the end of life, because these materials are reprocessable, and also they enable to the reparation instead of the replacement, and so this allows the reuse, so to speak. And additionally, we are reducing the electronic waste. In BIOMAPS project, we aim for different prototypes. For example, the ELF labels for injection molding integration. These prototypes will be used in combination with the automotive part, as I saw a couple of slides before. Also, interactive electronic labels for medicine packaging. Consumer goods bottles with integrated label, and also illuminated jacket with logo. And so the goal of BIOMAPS, and especially this task on the development of these demo use cases, is to demonstrate that B-trimmers are innovative materials that are very beneficial in order to make a better end of life, because we will first reduce the waste, since these materials are recyclable and reprocessable, and so we are also going to lower the raw material use and the environmental footprint, and all this maintaining the performance of the materials.
Thank you, Rafael, for your presentation and for all this information about the future of these demo cases and of the application of the industrial applications of B-trimmers. We are almost ready to close this presentation, but first of all, we will ask if there are any questions for all the presenters that today gave us some more information about this topic. Here we had the reply from the audience to the first poll. So we hope, especially for those who were not aware at all about B-trimmers and about the difference between bio-based and biodegradable materials, if they now are more involved and engaged in these topics. In the meantime, I can read to the presenters some of the questions that just arrived. So there is one question for Anna. You mentioned industrial and home composting. Will B-trimmers be able to be composted at home, and how?
So right now we don't know what will be the behavior of these B-trimmers. The composting will be the key industrial asset for the eco label for these new materials. But for the research, we have to check first with very specialized bacteria because that will give us an idea of what will happen at the composting level. So you have to take into account that we have a project that takes 3 years total, and we have to assess that very fast. So we cannot go for the 6 months required for composting. So that is why we have to design specific methods to assess the biodegradability, and then we can go to the composting. So at this time, we really don't know. Is it true that long chain PHAs are so far being described as less biodegradable than short length? And we are going to work with medium to long length. But I also have to say that I'm very much concerned about the degradability methods that have been used so far for the PHAs in the literature. So we hope to do better than they have done so far to assess this.
Okay, thank you, Anna. We hope that Federico's curiosity was fulfilled by your reply. And another question, congratulations for the presentation. It was very interesting. I was wondering, are there already any scientific publications related to this project? How I can find them? I think this is a question for all the team. So maybe we can say that all the scientific publication that will be published will also be reposted on our website in the section dedicated to the news and events, if I am not wrong. So you can anyway browse our website, and we will give you all the references of the website address in few seconds. And this way you can read everything that will be published in the context of this project. And another question, thank you for the presentation. It was really complete and very interesting, thank you. I would like to ask that TRL you aim to achieve in this project, also considering the industry's need to maintain both low environmental impact and low production costs, which method or methods are you interested in using to extract PHA from bacteria? Additionally, are you interested in evaluating new waste substrates as well? Thank you again for the presentation and for the opportunity.
Yeah, the general TRL levels that we are targeting for is going from 3 to 6. So the 6 is the NTRL level for most technologies.
So we are not going to use only bacteria to degrade the new vitrimers. We are also going to use enzymes and mixtures of enzymes. And the purpose of doing this is to be able to close the loop, so that we use the products of the degradation to feed the bacteria. That is the final goal of the work package where we are working with. I think
it's true that this maybe refers to the question of PHA production. And
about extraction right now, I think that in the project we are not going to tackle that problem, the extraction of bacteria, but from bacteria. But surprisingly, the same bags we are using to obtain bacteria that can degrade the plastic, they can also be used to extract the polymer. Because if you feed these bags with PHA accumulating bacteria, they will remove the organic and secrete the PHA. So that is also a way to extract the PHA. Very environmentally friendly way to do it. But it's not within the scope of our project, I think.
Okay, thank you. And other 1 or 2 questions. Will be checked lifetime of vitrimers?
Yeah, there's not in the plan any like long-term tests of how it will or will it degrade on certain types of environments. So at the moment, this will be left as an open research question.
Okay. And the last one, at least by now, thank you for the very insightful webinar. For previous studies, for previous studied cases, will the degraded polymers be enough to yield the same vitrimers when fed to the worm/bacteria, do you need to feed it fresh starting materials together with the degraded products? I think again it's a question for Anna.
We are not directly involved in the last part, which is the feeding the bacteria with the products of the biodegradation. But the answer is very clear. We don't know, because this will be the first time that these polymers will be submitted to these new types of bituminized polymers will be submitted to biodegradation. So we don't know what the products will be and how the bacteria can use them. Yeah, of course, there are other options. As you mentioned, we can also take the polymers and see if the worm can eat it. And then we can recycle it in a different way. But still, our goal is to try to feed the bacteria with the products of degradation. And let's see if we are able to do it.
Thanks all for your questions. We are closing the webinar, and there is a small gift to you. There will be soon available our guide, the BIOMAPS guide to explore the structure and properties of vitrimeric biopolymer systems. It will be soon available, and you will receive your digital copy on your email. And if you are interested in following us on our social network and website, here you can find all our accounts. So we are on Instagram and LinkedIn, X, YouTube. Obviously, we have a website, and this is the mail if you have any doubts or questions, if you want to be in contact with us.
And the next event will be in Turin. We are organizing the BIOMAPS first workshop. This is an event in the middle of October, of the next October, and it's an in-person event. And we'll present, of course, the BIOMAPS projects and next results, but we will share it with the citizen and with the wide public. Also, speaking with companies, people from the world of manufacturing industries or from research, in order to present better and understand better how we can use these new families of materials. So we will send you details through newsletter, but also the news will be published on our website and or on our social media. So stay tuned about this next event. And that's all. So thank you for your participation, and see you on the next meeting. And thanks to our colleagues, to our speaker for your participation, for your presentation. Sorry. So thank you again to all of you, to our public.